Greetings, aspiring scientists. Welcome to my video today on organic chemistry, functional groups. I think it's going to be a long one. No idea how long this is going to take, but I'm just going to go till it's done and we go through all the groups. I want it to be all one video. Usually try to keep my videos under 1 hour, but who knows? Yeah, and I think this video is very important. There's a lot of functional groups to know in chemistry and in IB chemistry. So one thing I want to say is that we're in structure 3 of the syllabus. That means we're focusing on structure, properties, shapes, drawings, formula, those kind of things. But I am going to talk about reactions as well, because I think it helps connect these things together so that you're not just memorizing a list of things and facts, but rather you're trying to see how they connect to each other. But just be aware that although I'm going to say everything I know about all these compounds, if you're just studying structure right now, what you need to focus on is the structure, the 3D kind of shape, properties, names, those kind of things, not really reactions. Okay, so let's go to my slides. We are 3.2.2, classification of matter, organic chemistry, functional groups. So what does this mean? So in my previous video, I talked about organic chemistry, the importance of carbon atoms, catenation, chains, branches, rings, those kind of things. But I also mentioned that there are sometimes groups attached that provide certain functions. Those are what we would call functional groups. So functional groups are attachments to an organic molecule other than the normal aliphatic hydrocarbon chains. So if you would just have CH and CC bonds in an alkane, usually that's called an aliphatic region or an aliphatic molecule. Those are not considered a functional group because they don't really have a function, they just kind of exist. They provide the basic organic structure and organic properties, usually non-polar sort of chain sections. So they do have some function, but for some reason we don't really classify them as having function compared to the other groups. Anyway, functional groups usually appear as multiple bonded species like double bonds or triple bonds, and or heteroatoms. These would be anything other than carbon and hydrogen, so ON, Cl, etc. They provide regions of reactivity, polarization, and other things that gives each type of organic molecule its properties. So here are basically the ones that I would recommend that we learn for IB. It's a nice little summary slide made with Google Gemini. So again, if you really zoom in on these, you might find a little bit of weird sections, but I tried to fix most of the big errors. But if you see any others, let me know. I can put it in the description. But we're going to be looking at alkanes, alkenes, alkynes, arenes, alcohols, ethers, aldehydes, carboxylic acids, esters, ketones, amines, amides, nitriles, and one more that I didn't include on here, which is halogenoalkanes, alkanes with halogens attached. So this is what we're going to be talking about for the next hour or so. So we'll start with the basic one, which has no real functional group, alkanes. So I'm going to provide you with a general chemical formula for all of these. Alkanes are generally CnH2n plus 2. So however many carbons you would have in this, you have double that amount of hydrogens plus 2. This is also known as the homologous series formula. We'll talk about that in my next video, but it's very good to at least know how to get this formula and apply it to other molecules. If you don't remember this, I'd recommend you do remember this for alkanes, alkenes, and alkynes, but you can just take any alkane and check how many hydrogens there are compared to the carbons, and you'll always find that there are 2 more than double. Now for naming, alkanes always end with the suffix ane, ane. We'll get into naming in my next video, but I'll also just introduce parts of the naming on each of the functional group slides here. So we have an example, butane here, that would have 4 carbons and then hydrogens in every other space. So alkanes contain only carbon and hydrogen. They're commonly found in fossil fuels, such as coal, oil, and gas, things that we would pull out of the ground and use for energy combustion usually. These have very low polarity. Essentially, they are nonpolar. The carbon-hydrogen bond is not very polar, and all the vectors will cancel out their directions. They're also known as aliphatic. They don't have what we call an aromatic ring, which is like a hexagon with alternating double and single bonds, or conjugated around the hexagon. They're often used as solvents, starting material for complex molecule synthesis, and for combustion, of course. They're combustible, but they're not very reactive in other situations. It's difficult to kind of transform these. They need some kind of activation that I'll talk about in a second. So some other important points about alkanes. As I mentioned, they're found in fossil fuels underground. They tend to only be produced by sort of dead plant, bacteria, animal, organic matter that is covered up by certain types of land, I think usually like swampland or things that suffocate it and prevent oxygen from reaching it. And eventually that material gets placed in a highly reducing environment, we say. And oxygen is not very common, and it can even be removed from that organic material as it transfers itself to more stable bonds on other atoms and molecules. So in that highly reducing environment, we get carbon surrounded by these hydrogens, and these hydrogens donate their electrons over that 50% line, and the carbons get negative oxidation states. So the important part I'm talking about here is that this doesn't happen really anywhere else. It doesn't happen on the surface of Earth. There's a lot of oxygen around. It doesn't happen in plants and animals and bacteria. We generally oxidize things more than reduce them. So that's why these are kind of considered non-renewable energy sources, because they're only produced in highly reduced environments underground over millions of years. So we cannot easily make these again. Even though there is a lot of it underground, it's still non-renewable because it's not really being produced at any reasonable rate from sources that we know of. All right, so alkane complete combustion. We should know this. Alkanes can be burned with oxygen and some activation energy to get it started, a spark or something. High heat, we can then combust it to make CO2 and water, H2O. This is exothermic, always. So for example, for 1 mole of fuel of butane, we can react that with 13.5 moles of O2 to make 4 moles of carbon dioxide, 5 moles of water. That has an energy release of minus 2,877 kilojoules per mole. That's quite exothermic. Alkanes, especially the longer chain ones, will be some of the best exothermic reactions that we know of to produce a lot of energy. So that's good. We can also have incomplete combustion of alkanes. You'll learn about this more in the fuel section of this course, but when there's not enough oxygen, instead of 13/2, if we have 9/2 oxygen, we make CO instead, carbon monoxide. So CO, when we make that, it's less exothermic, only minus 2,658 kilojoule per mole will be released. And also carbon monoxide is very toxic to living organisms, especially humans. And then an important point, if there's very limited oxygen, even less than this, we won't make CO, we'll just make C, which is elemental carbon, like amorphous carbon, soot, the black kind of powdery substance you might see around flames sometimes. along with water. And there can be mixtures of these things. We can have CO2, CO, and carbon soot. Just depends on how much oxygen flow there is. So I'm talking about combustion for alkanes here, but this can apply to basically any other chemical and compound and functional group that I'm going to talk about today. So I want to just go over some general organic reaction vocabulary, even just general chemical reaction vocabulary. We can have substitution reactions where something that's attached to a molecule is replaced by something else. So if we use HCl on this alcohol here, this OH group, we can replace OH with Cl, and then the other H will go with that OH group to make H2O. That's a substitution reaction. We can also have addition, though, where there's sort of a space. Often double and triple bonds offer this space where something can be added onto the molecule. So here's a hexagon, cyclohexane with a double bond. We can just add a Br2 molecule across there so that there's a Br on each carbon then the double bond disappears. It sort of opens up, we say, to form these new bonds. We can also have elimination, which is kind of the opposite of that. If we have this cyclohexane with an OH group on it, we can add some acid and remove that OH group along with a hydrogen that must have been there. These are skeletal structures, so just know that there are two hydrogens here as well. And we're removing one of those along with this OH group to become H2O. And then this double bonded section will just have one hydrogen on each carbon. Okay, it's also important to know that the cyclohexene in this addition reaction also have these two hydrogens, and they are still attached at the end, like that. Anyway, that's beyond the point of just what I'm trying to make here. The naming systems: substitution, switching something; addition, adding something; elimination, removing something. Okay, and I got this picture from byjuice.com. Very good chemistry learning material there. So alkane activation with halogen substitution. This is another thing that alkanes can do. They can be activated by what we call halogenation. It will involve a halogen, a group 17 element. So we can substitute a hydrogen on an alkane with a group 17 element. Usually will be chlorine or bromine. F is possible, but it does not actually activate the alkane, so we wouldn't use it to do further reactions usually. We just use it to fluorinate it and create compounds with F in them. But this process makes a halogenoalkane, and this is the name that we should be using in IB, halogenoalkane. But in other parts of the world or other organizations, it's known as an alkyl halide. It's just switch the suffix and prefix there, kind of. Now, this is made with a free radical mechanism. There will be initiation, propagation, and termination steps there known. I'm going to go over those quickly. And here's what a balanced chemical equation for that radical substitution might look like. CH4 plus Cl2 goes to CH3Cl plus HCl. So it looks pretty simple there, but I'm going to go over the mechanism, which is like how this actually is made through collisions and transfers. Okay, so here we can look at the free radical substitution mechanism. You will have to learn this eventually, but if you're just studying structure now, it's not that important to really know what's going on. I'm just giving you some idea of how this happens. So it's important to understand the word free radical. What that means is unpaired electrons. It's not a stable configuration of basically any atom or molecule, but it happens through these mechanisms and transition states sometimes. So let's go through. First, the initiation step here. We have our halogen, diatomic molecule usually, and it will be separated by some input of energy, usually UV light, and it will make two halogen radicals. This is just like an atom of the halogen, like chlorine. So it has 7 electrons when that happens in the valence shell, but we're just going to show one on the outside to be that one unpaired one, because that's the one that's going to be doing some chemistry. So let's see. So we get the initiation, we make 2 Cl dot radicals, Cl atoms. Okay, let me pause. Now next, we can have propagation, is what it sounds like. It's like continuing the radical chain reaction. So our Cl dot that we produce with UV light can attack our alkane. In this case, it's just methane. It will pull off a hydrogen. Okay, these halogen radicals, chlorine radicals, are so reactive, they'll basically pull off an atom from anything nearby, whether it's a chlorine or a hydrogen or whatever. So it pulls off a hydrogen, but that will leave a radical on our alkane then. The radical still has to be somewhere because conservation of mass and particles, right? If there was a radical on the Cl to start, it must go somewhere. So it ends up on the alkane. This is why it's propagation. We started with a radical and we finish with a radical. Now there can be another propagation, propagation 2. What will that look like? In this case, our alkane radical that we produced, now it's the most reactive thing. It will pull off an atom from anything nearby. So I think it could even pull another hydrogen off a nearby other alkane and continue propagation, but it can also pull off a chlorine from another diatomic halogen that must still be floating around. And if it does that, it makes our target product. That's what we want to happen. CH3Cl, that's a halogenoalkane. Hydrogen has been substituted with chlorine. And when that happens, we'll produce a new Cl radical, Cl atom with an unpaired electron. And you'll notice that can just go back and do propagation 1 again. So we can have propagation 1, propagation 2, propagation 1, propagation 2. They'll just go in a chain reaction cycle. But eventually, we will reach termination. What does that look like? It's what it sounds like. It's where radicals will be disappearing. So if 2 chlorine radicals happen to collide, they can make a new single bond. 2 unpaired electrons makes a pair. That will end a chain reaction of radicals. We can also have the alkane react with a chlorine radical, alkane radical. I just noticed that my animation is missing some hydrogens here. This should have 3 hydrogens still. And then our radical unpaired electron there. So these can come together and make what is our target, the halogenoalkane, CH3Cl, which again, we want to happen usually. But the thing is, this will remove radicals. So if this happens too much, it will stop our reaction from proceeding and we won't get much more yield out of this. So this termination step tends to happen as the concentration of radicals increases or reaches some plateau. And eventually the reaction will slow down and stop once we run out of sort of halogen radicals and alkane radicals. But this is how we produce halogenoalkanes. A very useful step to activate alkanes. Alkanes might have sort of the chain shape or length that you want to start with, but you can't do much with them until you activate them in some way like this. Okay, next, alkenes. We're only on the second one and it's 20 minutes, okay. Alkenes are similar to alkanes. They have a general formula CnH2n. So if you have exactly double the amount of hydrogens, chances are you have an alkene. It has the suffix -ene, E-N-E. Simplest example is ethene, 2 carbons double bonded to each other with hydrogens in the other positions. These are commonly produced again from fossil fuels, coal, oil, and gas. They are non-renewable as well, I think. They also have low polarity. They're essentially nonpolar. And they're used as starting material for complex molecule synthesis. The good thing about alkenes is that double bond offers a place for addition reactions. We can add a wide variety of things, almost anything we want, onto the alkene and make a carbon something bond. These are still combustible though and moderately reactive. They're more electron rich even than alkanes because of that double bond. It's like an extra concentrated region of electrons in a small space. And if you've studied HL, you know that the double bond part, the second bond, is different than the first bond. It is a pi bond that is above and below the molecule, and it's very susceptible to being attacked by electrophiles. This is a good word to learn. Electrophiles are things that are attracted to electrons in electron-dense regions. Okay, so let's see some animation of alkene halogen addition. We're going to be adding a halogen on, looks like Br2 here, onto this ethene molecule, double bonded carbons. Now this is kind of an electrophilic attack, we could say, but one thing to keep in mind is that it's always the electrons that move. So it's actually going to be the electrons in the alkene double bond, one of the pairs, that will be moving on to this halogen. So what happens when that happens? One of these BRs in the Br2 will leave. It'll take that electron pair that was between them and become Br minus. And the other one will actually kind of form this triangular structure. It's called a bromonium ion. I don't really see this in the IB textbook, so you don't need to know this, but it is interesting and it is true. And one of the professors I studied with at university was the person to discover this, so I have a special interest in the bromonium ion. But this sort of meta-stable, slightly stable structure, triangle with a positive bromine ion, will determine what happens next. The Br minus now needs to attach to another section of the molecule, so it will come from behind, I believe. Come from behind this triangle structure, and its electron pair will attack. And that will lead us eventually to the final structure of the product, where we just have carbon-bromine bonds. Two of them have been made, like this. So you don't need to understand that method or that 3D kind of attack pattern that well, I think. Just understand we're forming a dihalogenated product here, halogenoalkane, 1,2-dibromoethane. So now it's a halogenoalkane from an alkene. Okay, moving on. This is often used, actually, this reaction that I just showed, to test for the presence of an alkene. Sometimes you might have some natural gas or something, or some thing you're trying to purify. You want to know, is it alkene or does it have alkenes in it? You can do this test. You can add halogen, diatomic halogen, pure element. We can dissolve some bromine in some water, makes it slightly orange. It doesn't dissolve well, but some of it will, enough to see. Then we can bubble alkene gas through that solution, and the bubbles will come in contact with the aqueous solution that has bromine in it. And then the reaction I just showed on the previous slide happens. We get a color change, because as the halogen is added onto the alkene, it's used up, and that halogenoalkane is colorless. So we see that color disappear. This test often appears on IB exams as well, when they ask how might you test for alkenes, or what is a reaction that halogens can do that is useful with alkenes. Okay, now there's many other things we can add to alkenes. We can just add hydrogens, like H2 gas. It's very difficult to do just by mixing the two gases together, but if we have a special surface, like a metal catalyst, we can call it, transition metals like nickel or palladium. I'll show you a little animation here that shows. So we have adsorption first. H2 is kind of attracted to the surface of the transition metal palladium, and that will weaken the bond between H's and form new palladium-hydrogen bonds. Same thing can happen with the ethene molecule. The pi bonds, or the double bond there, can be attracted to the palladium surface, and the double bond will open up and form sort of new carbon-palladium pseudo-bonds. After that happens, if these things are near each other, the hydrogens and the carbons from the organic molecule, we can have a transfer of the bonds from the palladium and hydrogen and palladium and carbon to hydrogen-carbon bonds. It's difficult to kind of see that here, but we're forming new carbon-hydrogen bonds as the ethane molecule begins to leave the palladium surface. It pulls hydrogens along with it sometimes. And then the final step will just be, these have a chance to be removed as well, and once they are, we can collect the gas, ethane gas leaves. Okay, it's difficult to really explain how these things get stuck and shift bonds and get released, but just understand that we have ways to control this and push them forward so that the reaction does go, the hydrogenation addition reaction. Okay, next. I also want to mention some things about hydrogenation. There's a lot of uses for it, and one of the main ones that you might know of, or that's used in the food industry, is hydrogenation of oils. So a lot of like vegetable oil and maybe seed oil is a liquid. You guys probably know it's used for cooking and seasoning and various things. But sometimes people want solid or waxy kind of fats. For example, butter or margarine. It's nice to have a kind of solidified form that you can spread on things, or offers a bit more structure to your cooking. So hydrogenated vegetable oils were a big thing when I was growing up. But there's kind of this error that can happen, or this unwanted product, which is we can form trans fats or fatty acids. Now we have to know that most vegetable oils they do contain some double bonds, but these double bonds will always have chains on the same side of the double bond. And what I'm talking about is, if you look at this section here, let me use red. This section here, this contains a carbon-carbon double bond, and the chains where the carbon chain continues are on the same side here. This is what's known as the cis configuration. On the other side, we have hydrogen, so there's not really any extension going on. But sometimes when we try to make like butter or margarine through hydrogenation, we'll break that double bond and reform it. And what we get then is a trans configuration where the carbon chains are on opposite sides of that double bond. And that doesn't seem like much of a change, but is a big change to structure and interactions between these molecules. So trans unsaturated fatty acids, that you can read on the left here, this is a hydrocarbon chain that contains at least one double bond where the hydrogen atoms are on two different planes of the molecule. Whereas usually the natural version, the cis version, contains at least one double bond where the hydrogen atoms are in the same plane, causing a bend in the molecule. So bent, or kinked as it's sometimes described. What this provides to the material is fluidity and liquid state usually. It's difficult a bit to explain how, but you can imagine if you have this sort of multiple kinked structure like this, These tend to not stack well with other molecules of the same thing. I mean, you can try, but they just won't generally come together that well and stack. But look at the trans chain. It's zigzagging and it's fairly consistent and it's fairly straight. If you have that shape, another one can come in very close, another one can come in very close, and we get interactions, heavy London forces between this, and it causes it to solidify as a crystal or a wax or gunk, you know, in your body, in your veins and arteries, blocking blood flow and generally having other effects, like I think raising your cholesterol, your blood pressure, those kind of things. So we realize how bad this is and we try to cut it out of foods and try to avoid hydrogenating in this way, I think, in recent times. If you're interested in that, go study more about it though. All right, other alkene addition reactions. We can also add hydrogen halides, like the acids that you probably know, hydrochloric acid, hydrobromic acid, hydrofluoric acid. HX, just ignore these colors. I think my AI assistant got this wrong, but we're just adding HX across the CC double bond. So we'll have a halogen added somewhere and then a hydrogen added on the other side. There are rules to where it will be added, but I think it's only really important to discuss that in the structure section of the course. Sorry, the reactivity section of the course. We can also add water, H2O. Again, ignore the colors, but we'll add an OH group from water onto one carbon and an H to the other side to make an alcohol. That's a new functional group we haven't talked about yet, but it's coming soon. We can also have polymerization. I've made a video about this already, but just a reminder, we can have ethene like this just react with itself as double bonds open up and link with neighbors, forming new carbon-carbon bonds. We can make hundreds of thousands of units long chains, and they can be attracted by London forces and entanglement and things to make polymers that we usually know as plastics. All right, anything else? Nope, so that will bring us to the next group, alkynes. Alkynes have the general formula CnH2n-2, the suffix -ine, Y-N-E. Here's an example, propyne. So you can see there's a carbon-carbon triple bond in there for propyne. These are produced in small amounts, from fossil fuels. Again, you'll find a little bit of these maybe in coal, oil, and gas, but they are more rare than alkanes and alkenes. I think they have low polarity as well though, not much going on, non-polar. They can be used as starting material for complex molecule synthesis. Because they have that triple bond, it offers sort of a double space for additions. They're combustible as well and moderately reactive. The alkyne section is electron rich, very similar to alkenes. Now I don't have much else to say about alkynes because they're very much similar to alkenes. The difference is a lot of these addition reactions could happen twice, right? You could add like 2 H2O molecules on it, or a halogen, diatomic halogen plus a water molecule onto it, form multiple functional groups. And alkynes combust with large exothermic energy release. If you've ever seen like an acetylene explosion or acetylene welding torches, they're quite exothermic when these are combusted. All right, so I do want to talk about halogenoalkanes. These have the general formula CnH2n plus 1x. So instead of H2n plus 2 for an alkane, one of those hydrogens is replaced just with X, where X is a halogen, fluorine, chlorine, bromine, iodine. Here's an example, 2-chlorobutane It just has a chlorine attached on the second carbon instead of where there used to be a hydrogen. But these do only contain carbon, hydrogen, and halogens, F, Cl, Br, or I. They're usually polar, like medium polarity, medium high. They can be used as starting material for complex molecule synthesis because the carbon-halogen bond for chlorine, bromine, and iodine is quite weak. It can be changed to something else. But CF bonds are highly stable and unreactive. These are combustible as well, but they'll often make chlorinated combustion products, or halogenated combustion products, which are not very environmentally friendly. So we don't usually combust them on purpose. All right, so what's a reaction we can do with a halogenoalkane? We can make an alcohol through something called nucleophilic substitution, where we can have a hydroxide polyatomic anion come in. It'll come in behind the halogen group on our halogenoalkane and attack there. We'll form this little transition state, and it will kick out the halogen as its own anion. So the halogen will take the pair of electrons from the carbon, but the carbon gets a new pair of electrons from the hydroxide. I just noticed that the hydroxide really should have 3 lone pairs around that oxygen. All right, so this will produce what we call an alcohol functional group in class from a halogenoalkane. This is a good example of a nucleophile, the OH minus group. Nucleophile is the opposite of an electrophile. It's attracted to positive regions that are lacking electrons, electron density, and it can form new bonds there. Nucleophiles themselves are electron rich. The leaving group is known as Br minus. It's sort of good at leaving and taking its pair of electrons, and it's stable in an aqueous solution just by itself, so it can leave. Okay, the details of that will be important in the reactivity section, but just for now, you can see how an alcohol might be made all the way back from an alkane. Speaking of alcohols, let's introduce that functional group. Alcohol, CnH2n plus 1 OH. So a hydrogen has been replaced with an OH group. These have the suffix ol, OL. An example would be ethanol, the one you probably know that's in alcoholic beverages. And I'll also introduce now that we have functional group names for many of these. So the name of the OH group is hydroxyl. That's different from its class name of alcohol. So you have to know both. Alcohols contain carbon, hydrogen, and oxygen. They're usually produced by oxidation of other organic molecules, such as alkanes or alkenes. They have high polarity. They can also have hydrogen bonding, right? We have OH bonds. So that will cause them to stick together very well and have sort of higher boiling points, potentially. They're combustible as well. We can actually use them for fuels. I'm sure you've heard of people adding ethanol to their vehicles sometimes. Moderately reactive. The OH group can do certain things, certain reactions. They can also participate in condensation reactions to form esters with alcohols, or ethers with alcohols and esters with carboxylic acids. Those are groups I will introduce later on in this video. But condensation is a word you should get used to as well. It means coming together to form a new link, and when that link is made, a water molecule is removed from the system, from your molecule. Okay, let's see a few of these. So I'll just review again nucleophiles and electrophiles, words that you should really get used to. Nucleophiles are small atoms or compounds which attack areas of positive charge density. Nucleophiles often contain high negative charge density areas, such as negative charges or lone pairs. Small bases like OH minus, pretty small. They're often good nucleophiles. Then oppositely, electrophiles are compounds which have a lack of electrons, areas of positive charge density, and they seek out vulnerable electrons such as pi electrons. Those would be double and triple bond electrons. So of course we can combust alcohols as well. You can combust ethanol with 3 oxygen molecules, produce 2 CO2s and 3 H2Os. But this delta H is only 1,367 kilojoule per mole. That's like about half of what something like butane we saw was. So alcohol and other organic fuels are alternatives to gasoline, and they have advantages and disadvantages. What might some advantages be? Well, this is renewable. This can be made by plants, bacteria that would do photosynthesis to connect carbons together and then have an OH group attached. I think ethanol is made more from fermentation of glucose that was made from photosynthesis, but from the start, it came from photosynthesis, which pulled CO2 out of the air. That's sort of the opposite of releasing greenhouse gas, right? We can take CO2 out of the air, make this ethanol fuel, and then combust it. We will release CO2, but the net release is essentially zero because we take it out of the atmosphere first in photosynthesis. Another good point is that ethanol is a liquid that's not extremely volatile compared to like gasoline. So that might make it easy to handle. But disadvantages, of course, are just its energy output. That kilojoule per mole minus 1,367. Not as much as things like gasoline, so we would have to burn more ethanol to get equal amounts of energy. And there are many more other advantages and disadvantages. We can also oxidize alcohols further. This can get pretty complicated, so I'll go through some possibilities. We can oxidize an alcohol with a strong oxidizer such as potassium permanganate, MnO4, shown in purple here because it is very purple if you see it. Now, these reactions will make more sense if you've studied redox reactions in the reactivity section, but I recommend you come back here and look at this after you've studied that. For now, we can just look at these half reactions. There's an oxidation of our alcohol into COOH group at the top here, and the reduction will be happening on the metal. It's really the manganese, the Mn, in this oxidizing agent that will change its oxidation state. It will go from +7 in MnO4 minus to +2. So right there, there's a 5 electron difference, and we can use that in this reaction to end up with our oxidized alcohol. So the overall reaction, when you add those two together and balance it properly, is shown here under that overall reaction. But if you're just curious about what happens to our organic molecule, ethanol can go to ethanal. That's a new functional group called an aldehyde I'll talk about later. And we can go even further to a carboxylic acid, ethanoic acid, which is also known as vinegar. So some important points here. O2 in the air is generally not strong enough to do this. So if you just have some ethanol laying around, it's not going to become ethanal or ethanoic acid, at least not in the time scales of human life. So we need stronger oxidizing agents such as potassium permanganate. And secondary alcohols will proceed differently here. Okay, ethanol is what we call a primary alcohol with the oxygen on the end of the carbon chain. But if it were in the middle, we get different reactions, so just be aware. So eventually you'll have to know these like chemical equations in this redox process before you take the IB exams, but we'll learn about this more in reduction and oxidation section of the course. Now I do want to mention you can also do this with another strong oxidizer, potassium dichromate, K2CR2O7. Then the oxidation and reduction reactions will be shown here. the half reactions on the top, add them together, you get the overall reaction underneath. So in this case, chromium, if you check its oxidation state, I think it's +6 in the dichromate ion there, and it will go to +3. And there are 2 of them, so we need 6 electrons for that process. So this is where the redox reaction happens. But again, our organic molecule, the only effects that we will see is that it goes from ethanol to ethanal to ethanoic acid, and it's oxidized each time. You can check the oxidation states of carbon in that functional group as well. The COH to start with, that carbon is -1 oxidation state. It will go to ethanal as it loses 2 hydrogens, it goes to +1 oxidation state, and it goes to ethanoic acid then, and it will have another oxygen added, but it goes to +3. All right, so those other functional groups discussion will be coming soon. But I do want to mention some notes about these oxidizers. These oxidizers, first of all, are not catalysts. If you've studied rates in reactivity, you'll know that catalysts sort of speed up reactions, but they are not consumed. They're regenerated at the end of some mechanism or process. But these oxidizers will be consumed. They're essentially reactants in the reactions, in the redox reaction. So they will be consumed and transferred to different oxidation states. Potassium permanganate is stronger, KMnO4, and it can be selected if your final desired product is that carboxylic acid, the heavily oxidized functional group. Potassium dichromate, though, offers a bit more control. It might be slower, but it may wish to be selected if the target is the aldehyde instead, that middle step in the oxidation chain. Further conditions required for these reactions, these oxidations, are usually heat. You got to heat them up a bit to get things going. Acid, H+ ions, maybe like some H2SO4. I do think permanganate can oxidize without acid. It's strong enough, but it will oxidize further, faster, and better with some acid added. And then we need, I've said heat, but we got to set up what's called a reflux, which is where we will heat up our solution even beyond the boiling point of our liquids like ethanol to get things really going, or distillation. Distillation will heat it up as well, but it will allow us to separate things as they begin to boil. We can collect them in different flasks. So let's go through some of those setups. I don't think I've ever talked about reflux in my videos before, but we can have a round bottom flask, put on a heat source, heating mantle maybe. So our liquid will heat up, start to boil, and it will go out the top. But what we do is attach a condenser, a special piece of glassware. It's kind of a tube within a tube. Then that middle tube section will flow water through that, push water through, cold water in the bottom, and our hot vapor will heat it up, so the warm water comes out the top. But the point is we want to capture all of the vapor that's boiling, recondense it back into liquid, and let it fall back down. But we do leave the top of that condenser open to atmosphere just in case some crazy reaction or explosion or bubbling happens. We don't want pressure to build up in our round bottom flask and it might, explode and send shards of glass and toxic chemicals around. We'd rather it just go out the top in an emergency. But this is a way that we can heat up a reaction above its boiling point because it will boil and then recondense. So this is what we would do, I think, if we want to get the carboxylic acid, the most oxidized version of the alcohol. But if we want to be a bit more careful, capture other products like the aldehyde, we would instead just take that condenser and turn it to the side so that whatever comes out of it doesn't go back in the round bottom flask, but goes into a separate collecting flask, the receiving container. So if we heat up our mixture with the oxidizer, to medium kind of heat, and we get first step oxidation to the aldehyde. We can then collect it in the condenser, collect it in the receiving flask, and try to get the best yield we can. It's still going to be difficult. We're probably not going to get that high a yield, but this is one of the best ways. All right. Now, oxidation of secondary alcohols. So as I mentioned, everything I talked about before was when the OH group is at the end of a carbon chain. But what if it's in the middle? Suppose we have a propanol here where the OH group is on the second carbon in the triple carbon chain. That's known as secondary carbon. And it will proceed similarly but slightly differently. We can add our oxidizing agent, potassium dichromate or potassium permanganate, and we will end up removing 2 hydrogen atoms from our structure, and we get a carbon-oxygen double bond in the middle. So it looks very similar to the aldehyde, and it is, but here it's known as a ketone, propanone ketone. And ketones cannot be further oxidized. We cannot, keep adding oxidizing agent and try to get more oxygens on this central carbon. It just doesn't go any further. Similarly, if you had a tertiary alcohol, that would be something like what's known as tert-butanol. 3 CH3 groups attached to a central carbon that has just one OH group. That can't be oxidized any further at all. Can't make a ketone or an aldehyde or a carboxylic acid. So it does not go. All right, what else? So we can also just bring alcohols together. It doesn't even have to be the same alcohol, but in this case, this example I'm showing, it's 2 propanols. If we just heat this up, add some acid, and remove water as it's being released, we can condense alcohols into this linked new molecule known as an ether. Oops. So the general name for this is an ether. And the actual name for this, I think, would be propoxypropane. Now, this reaction is actually reversible as well. That's why I have an arrow going to the left. It can fairly easily return to being multiple alcohols if water is just added back and reheated and we push things backwards. So if you really want to make ethers and push this forward, you gotta be removing water and heating this up and boiling it off. Or maybe not boiling it off because the ethers also boil, but somehow removing H2O from our mixture. Okay, we'll talk about ethers more later. We can also have esters. Excuse me. Esters will be a similar condensation, a grouping of OH groups, but instead of alcohol plus alcohol, we can add it with a carboxylic acid OH group. And we'll take H2O from these. We'll take H2O from there and link the R's together with an oxygen then. R is just, whatever, usually a continued carbon chain. But we get the ester linkage, that is C double bond O linked with O, linked with the rest of the chain. And H2O again will be removed. Again, this is reversible, so we have to keep removing water or else water will act as a reactant for the reverse reaction. But this kind of linkage appears a lot in biology. And, very often it will be linked and then unlinked in different sections or different processes. Ester is very important though. We'll talk about those later. And then just showing, again, with some 3D models, so you can maybe see a little bit easier. We have an alcohol ethanol in the top left, and then a carboxylic acid ethanoic acid. H2O will be brought together and removed. That's why it's called condensation. And then these will just be linked together through one oxygen. So we have that carbon, oxygen, carbon, double bond oxygen, and then the remaining chain on the right. And water is removed. It's called esterification, Fischer esterification. All right, so let's talk about all those things I just introduced. Aldehydes, CnH2nO, general formula, suffix al in naming. Example, ethanal. Functional group name of this is carbonyl, carbonyl group. So aldehydes contain carbon, hydrogen, and oxygen. They are produced by partial oxidation of primary alcohols at the end of a chain. They have high polarity for sure, carbon-oxygen double bond, but they cannot do hydrogen bonding with themselves. There is no OH bond anymore, which is interesting. Alcohols could do hydrogen bonding, but aldehydes, the more oxidized version, even cannot with themselves. These are combustible, these are moderately reactive. The aldehyde carbon especially is positively polarized and sort of weak to attack by nucleophiles. This can even be further oxidized to a carboxylic acid by replacing that hydrogen at the end with an OH group. So that's all good information, but do you guys know about aldehydes? Well, generally, I think they can be a wide range of pleasant to deal with compounds to terrible, terrible smelling and toxic compounds. I think formaldehyde, which is methanol, is used to preserve body parts. The aldehyde version of ethanol is known as ethanal, and it is what will cause many of the symptoms of hangovers after you've been drinking alcohol. Not that any high school IB students should have been drinking alcohol, but someday you might know how terrible of a toxic chemical it is. It's not very pleasant at all, but then you have things like, I think cinnamaldehyde is in cinnamon, gives very pleasant sensory feelings usually. So it really depends on what is attached to the rest of the aldehyde, but it is in many things that you know of. All right, so just remind you that the way that we might get aldehydes is partial oxidation of an alcohol. So that ethanal in the middle of this slide, in the middle of this chain, we need to distill this very carefully under controlled heat and controlled reaction conditions. Probably very difficult to get any kind of good yield of an aldehyde through this method anyway. All right, carboxylic acids, these are CnH2nO2, suffix oic acid. So here's an example, propanoic acid, 3-carbon chain, and on the third carbon, C double bond O, COH also attached. Functional group name of this, carboxyl, carboxyl group. These contain carbon, hydrogen, and oxygen. They're produced by heavy oxidation of primary alcohols. They have high polarity. They can have double hydrogen bonding too. I've talked about this in my, I think, covalent physical properties or intermolecular forces video. They can hydrogen bond in the lower section, OH to O, and then in the upper section, O to OH on another carboxylic acid to form kind of dimerized bonds. They are combustible, reactive, especially because of that weakly acidic hydrogen. The OH group in carboxylic acids releases H+ fairly well, almost nothing compared to like sulfuric or hydrochloric acid, but as weak acids go, they can release, carboxylic acids can release H+ and lower the pH of solutions. They have high intermolecular forces, that means high boiling point, surface tension, etc. And they can participate in condensation reactions to make esters, as I mentioned. So carboxylic acids, nothing really coming to mind other than vinegar. So vinegar, it tastes acidic, right? Sour, we generally associate with acidic things, and so we associate it with carboxylic acids as well, usually. Now, if we want a carboxylic acid, we might rather choose potassium permanganate, the stronger oxidizing agent, and just reflux this, heat it up for a decent amount of time, push everything to ethanoic acid, heavily oxidize it. Okay. Next, ketones. This is, again, what will happen if we try to oxidize the secondary alcohol, the OH group in the middle of a organic chain. CnH2nO, same as aldehydes. Suffix, though, is -one, O-N-E. Functional group name, carbonyl. This is the same name as aldehydes. So a carbonyl group can be at the end of a chain or in the middle, and it will produce different classes. This is where things get kind of complicated, right? But this contains carbon, hydrogen, and oxygen. It's produced by oxidation of secondary alcohols. Again, we don't have to worry about over-oxidizing because it cannot really be oxidized anymore. These have high polarity, but no hydrogen bonding with themselves, similar to aldehydes. They're combustible, moderately reactive. The ketone carbon is positively polarized, and nucleophiles will be attracted to it. Example, propanone here. This is acetone, or often used as makeup remover or paint thinner. It's very, very good at dissolving a wide variety of things, and it's very volatile, so it will evaporate quickly. Oxidation of secondary alcohols. So just showing a little visualization here again. I've already shown this slide, but just to review. Ketones cannot be further oxidized once they get here. Similarly, tertiary alcohols do not react with oxidizers. Okay, ethers then. I've talked about this already. They're made from alcohols, but general formula, CnH2n plus 2O. Just they're like two alkane chains linked together, right? And they have the name, not a suffix, but something oxy, something else. And the functional group name of this is alkoxy, an alkoxy group. So here's an example, ethoxyethane, also known as diethyl ether. This is produced by condensation of alcohols. It doesn't always have to be two of the same. You can have different chain lengths on each side of this oxygen. These have kind of medium polarity. The oxygen definitely pulls electron density towards it, but no hydrogen bonding with itself. There's no OH bonds. And these can be hydrolyzed, we say. That's the word for chopping it back up into two alcohols by adding water. I'm not really thinking of any ethers that are commonly known. Like, it used to be used as an anesthetic, diethyl ether, I think, in medical situations, but these are extremely flammable, especially the light ones with the small carbon chains. They're some of the most volatile and flammable substances. Then just a quick reminder, we can condense two alcohols together. Here's propanol being condensed. This is reversible. If there's too much water around and heat and acid, this will go back to alcohols. Esters then, CnH2nO2. These have the formula something ill, something O8, complicated name, but the missing sections will be containing information about the chain lengths of the carbon chains attached. So these contain carbon, hydrogen, and oxygen. They're produced by condensation of an alcohol with carboxylic acid. They have high polarity, but no hydrogen bonding with themselves, actually. Despite two oxygens, there is no OH bonds once an ester has been made. Excuse me. These are combustible as well, moderately reactive, and they can be hydrolyzed, especially, back into alcohol and carboxylic acids if there's water and heat and acid around. Esters, how might you know them? These are generally really associated with flavors and sort of fruity sensory compounds in like bananas, strawberries, berries, whatever. Flavoring agents very often use esters. So reminder, we can condense alcohol and carboxylic acid together to make the ester link. The reaction is reversible though. Okay, moving on to something different, aromatics. So first class is called the arenes, CnH2n minus 6. So this is heavily unsaturated, we say. It's missing a lot of hydrogens that could have been on it. So benzene is a suffix that will be added. Here's an example, methylbenzene. This just has a CH3 group attached to the hexagon that is benzene. Functional group name though is phenyl. No idea why or where that came from. It's very different than the word benzene, but the group name is called phenyl group. These contain carbon and hydrogen only. It's produced by oxidation of other organic molecules and often found in fossil fuels. Now you might say, how is this an oxidized organic molecule if there's no oxygen in it? Good point, but we can also oxidize things by removing hydrogens. And this is like a hexagon that has had many hydrogens removed from it. 6 hydrogens removed, it looks like. So that's why it's still considered oxidized. These have very low polarity, they're nonpolar, they are combustible and somewhat reactive. They still contain a lot of electrons in a small space. They're electron dense and they have sort of electron density above and below that may be susceptible to attacks. They have delocalization all around the ring. They have pi electron clouds, we say, where those double bond electrons exist above and below what we call the aromatic ring, the benzene ring. Now, I don't have much to say about this. There's a whole big topic in HL about benzenes and aromatics, but for now I'll just say some common reactions that they can do are called electrophilic aromatic substitution. So since benzene rings, you can also draw them as a hexagon with a circle in the middle to show conjugation and delocalization all around that system. Well, that's very electron dense, so something like electrophiles will be attracted to that and potentially attack and form new bonds. So we can add a halogen onto a benzene ring using electrophilic aromatic substitution. Br2, along with the catalyst FeBr3, this will generate very positive Br plus cations or positively polarized Br regions that are strong enough to attack the benzene ring and kick off a hydrogen, which will be picked up by Br minus, the other half of that Br2 molecule. So we get, in the end, a substitution of hydrogen with bromine. And you can do maybe a lot more with brominated benzene rings, further reactions, but we're not going to go into that. But aromatic benzene rings are electron rich. They can react with electron poor species, electrophiles. In this example, Br2 is the electrophile, especially when it becomes positively polarized, one of those bromines. And FeBr3 is a Lewis acid catalyst. So it will actually be regenerated and not consumed in this, ideally. And actually, H2O would interfere with this reaction, I think, so it needs to be done in a different solvent, less reactive solvent. And again, this diagram from Baiju's chemistry. That's all for benzene for this video, though. All right, amines next. Cn, H2n plus 3n. Suffix amine. Functional group name, amino. This is where we start to introduce nitrogen. So our compounds can contain carbon, hydrogen, and nitrogen. In amines, well, they will contain carbon, hydrogen, nitrogen. These are high polarity. They can have self-hydrogen bonding for primary and secondary amines. As long as there is an NH bond in the molecule, it can hydrogen bond with itself. These are combustible and reactive for sure. The lone pair on that nitrogen, especially, you have to realize in this nitrogen, there's always a lone pair. That's very negative charge density and basic, we can say. It can react with other things. It will act as a base or nucleophile. So the example I have here is methanamine. If you've ever watched Breaking Bad and the scene where they steal a bunch of chemicals from a train, they're stealing this. Turns out getting a lot of this pure and stable liquid is not that easy, so they have to get it from somewhere. The only place they could find it was on that chemical train shipment. But it is very useful for chemical synthesis, amines. Trying to think of where else you might find it. I think it's just often in meats and fish, especially as they start to break down and decompose. Amines might be released and smell pretty fishy and terrible. Now, we can do a reaction between carboxylic acid groups and amine groups, another condensation. So we can take a hydrogen from the amine and an OH from the carboxylic acid. If those come together and collide, they can make an H2O molecule be released and will form a new link, which will have a carbon-oxygen double bond directly connected to an N, usually NH, and then R for the rest of the chain. These R groups just represent some continued organic molecule. This makes what we call an amide bond in chemistry, or a peptide bond in biology. If you're studying biology as well, you would know this is what makes up proteins, peptides and peptide bonds. So this is what would link amino acids together in a chain that is a protein in biology, hugely important. But we often use it in chemistry as well. So we can just heat up the carboxylic acid and amine, maybe add some catalyst or enzyme or coupling reagent, help it go along. Now, this is a condensation reaction very similar to esters and ethers, so it will go in reverse if there's too much water around, and we have enzymes and catalysts in the body that will help cut these up when it's needed. Yeah, so just those points underneath, basically I said already. Amide bonds, very important when we condense amines and carboxylic acid. Okay, so specifically talk about amide. Amides are CN, H2N plus 1, ON, general formula, suffix amide. Functional group name amido. These contain carbon, hydrogen, oxygen, and nitrogen. They come from condensation between carboxylic acids and amines. They have high polarity, usually hydrogen bonding, as long as there's an NH group still remaining, an NH bond remaining. They're weakly combustible, although, not really, right? You can go to the store and see protein powder. It's not really worried. We don't worry too much about it, like combusting. But with enough heat and the right conditions, it will probably combust into CO2 and maybe N2 gas. But these are moderately reactive. Again, they can be hydrolyzed. They often have different things attached that will affect their reactivity. And they make up the protein chains. That's the important thing. Peptides, they can be hydrolyzed by enzymes and other things in living organisms. So here's my example, methanamide, sort of the most simplest version of an amide. NH2 on one side connected to C double bond OH. All right, then the last one I have, this one's actually not usually in IB textbooks or in the subject guide, but it appears on exams so much that I feel like we should know it. It is the nitriles, CN, H2N minus 1, N, and the suffix is a nitrile, like methane nitrile, ethane nitrile, propane nitrile, and so on. This contains carbon, hydrogen, and nitrogen. High polarity. Some of these, like dipole moments, are some of the highest I've seen, but there's still no hydrogen bonding with itself because there's no NH or OH bond. They are combustible, moderately reactive. The CN bond might be able to do some addition reactions or something. So here's my example, ethane nitrile, carbon-nitrogen triple bond, you can see. That's sort of the defining section of nitriles, carbon-nitrogen triple bond. I think these can also be potential nucleophiles as well. And that brings us to the end. So I just want to go over this summary slide. Although that is a ton of information I just said, and you should eventually know most of it before you take the IB exam, again, what you focus on when you're studying structure in the Structure 3 section is the shape, the geometry, the names, and some of the properties. Not necessarily all the transformation reactions. Those will come later. But I also want to mention that these things are linked together, often through oxidation and reduction pathways. Okay, so let's go through this pathway. You might start with an alkane that has carbon in the -3 oxidation state. You can then remove 2 hydrogens, H2. We didn't really go through how to do that, but it's the opposite of hydrogenation. It will be known as dehydrogenation. Remove some hydrogen, make an alkene. Carbon there is in the -2 oxidation state. You can then add an H2O across that double bond to make an alcohol. When we do that, carbon on the alcohol section will go to -1 instead. We can then use an oxidizing agent to remove 2 more hydrogens. We'll get the aldehyde. Carbon on the aldehyde group is +1 oxidation state. We can then add another oxygen through our oxidizing agents, potassium dichromate or manganate, whatever. We'll get a carboxylic acid. In that case, our carbon is +3 oxidation state. And then it kind of seems like it's at the end, but you can always go the final step, which is to combust it. Combusting it to CO2 will create the absolute most oxidized version of carbon, +4, where all of its electrons in the valence are essentially given to oxygen. So we can do combustion or what's called decarboxylation. Sometimes that happens as well, where just the C double bond O, COH section of a carboxylic acid loses its hydrogen and then loses the whole final carbon as a CO2 group leaving. So you can see the most reduced versions of these are on the left. The most oxidized versions are on the right. This can go left to right and even right to left. As long as you still have that carboxylic acid, actually, you can use reducing agents. Add more electrons and more hydrogens, remove oxygens to go backwards through specialized reactions. So I think it's helpful to see these as steps on a pathway instead of just memorizing individual functional groups. The other ones we talked about are mostly like linkages, right? Ether, ester, amide linkages, or they might be nitrogen-containing compounds, amines, amides, nitriles, you should also remember, and also halogenoalkanes. I could have drawn this step instead, starting with a radical transformation to a halogenoalkane, and then substitution of that halogenoalkane into an alcohol. I just chose to go more of an alkene route instead. So very important. And I think that will bring me to the end. We're almost at an hour and a half here. But I do hope you found what you were looking for somewhere in this video to learn about functional groups. Everything about them that I know of, pretty much, I have talked about. So in my next video, I will talk about homologous series and just a few more things about the structures of the more common organic molecules. All right, thank you very much for listening. We made it through. See you next time. Bye-bye.